All right, hello Algebra 2. You guys have a quiz tomorrow, so I thought I'd throw a video together for you. We'll see if it helps. Starting here, you guys are graphing exponential functions. Now this first function has a base of e, and we know that e is approximately 2.718. And I know you guys were asking in class if you could use your calculator, and the answer is no, you can't use a graphing calculator. And the answer is no, you can't use a scientific calculator. And the answer is no, you can't even use a four-function calculator apparently. So here's what you will do. You'll go ahead and just let e, just round it to 2.72, and then just work with it in that form. And really all you'll have to do is maybe multiply this by 2 or multiply it by 3. Like, it'll be pretty simple. So don't be too stressed about it, and I'll show you what I mean as we go through this. But here goes. I want to sketch this guy's graph, and I want to use my graph to find the properties. So I don't know about you, but the first thing I'm doing is the asymptote, because I know the asymptote is just my horizontal, my vertical translation, I should say. So this -1 means my asymptote is going to be, well, a horizontal asymptote. And it'll be dragged down to where y equals 1. So right here, I'll draw a dotted line. That is my horizontal asymptote. Then I want to plot a couple points. So the points go right here. We know we want to choose a point, one point where the exponent comes out to be 0. Then we want a point where the exponent comes out to be either 1 or -1. Sometimes we use -1, but with e, it's going to be ugly no matter what, because e is already an irrational number. So we may as well just let it be 1. That means if I'm trying to get an exponent that equals 0, well, 3 minus 3 would be 0. So we're pretty obviously going to choose 3 for our x. Then if we want to get 1, then we're going to let x be 2. Okay, so the very good news is when you plug in 3 to this function to find your y value, you get 2 times e to the 3 minus 3 minus 1. Well, 3 minus 3 is 0, of course. So that's e to the 0. So I don't need a calculator for this, because e to the 0 is 1. So that's 2 times 1 minus 1. So 2 minus 1 is 1. So you know the y coordinate that goes with 3 is 1. And then we can plot our point at 3, 1 right there. Now with 2 is where it's a little tougher. This time you maybe would wish you had a calculator, but you're not going to have one. So here goes. We're going to do f of 2. And this time f of 2 is going to be 2e to the 3 minus 2 minus 1. That means it's 2e minus 1. Well, 2 times e, I mean, that's pretty doable. You just grab e, which we said we're rounding to just 2.72, and then you're going to multiply by 2. And just multiply like you're back in 4th grade or whatever, 3rd grade when you learned how to multiply. Just multiply, you get 4. 14, put down the 4, carry the 1. That's 4 plus 1 is 5. There's 2 decimal places, so 5.44. So it's 5.44 minus 1, which means it's 4.44. And when you're giving those coordinates, you can actually just round to 1 decimal place. So 4.4 is fine, because we're not giving you a calculator, so 1 decimal place is plenty. And then just plot it as accurately as you can. If 2 is giving 4.4, then that would be about halfway between 4 and 5. So that's looking good. And now that I've got 2 points and my asymptote, I can see that my graph wants to come down, 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 hitting those 2 points, and then turn and be asymptotic. Now, you have to find the y-intercept anyway, so you might want to find it. Maybe if the y-intercept is, if it's 10 or a little less than 10, then it'll still be on our grid. But it looks to me like it's going to be a lot greater than 10, and it'll be off our grid. But you might want to know that, so you can shape your graph a little bit better. So let's do that math. So I don't really need this math anymore. I'll bring it down here, I guess, and shrink it, just to remind you. Oh, you can't see it. Then I'll put it here, over my head. All right, so now in the space we've got over here, let's find our y-intercept. And again, just like any other y-intercept, remember that if you're on the y-axis, like look at this point, if you're on the y-axis, it means that your y value can be anything. I can be up, 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 I can be down, 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 but your x literally has to be 0, because if you're on the y-axis, you can't have gone left, you can't have gone right, you must be at 0. So that's the trick to calculating it, is you plug 0 in for x, which means your y-intercept will always be f of 0. So what is f of 0? F of 0 is gonna be 2 times e to the 3 minus 0 minus 1. And so that's 2e cubed minus 1. All right, so I'll be the first to admit that if you don't have a calculator, this would be pretty annoying to try to calculate. So I'm not going to ask you to do 2.72 times 2.72 times 2.72. What I'll ask you to do instead is just leave your answer in this form, okay? You could sort of eyeball this if you wanted. If we just pretend that 2.7 was like 3-ish, then this is 3 cubed for 27, doubled is 54, minus 1 is 53. So it's not quite that big, but it's definitely off the grid like I thought it would be. So it's not going to help us sketch our graph. So you may as well just give the coordinates as, when x is 0, the y value is 2e to the third minus 1. And just call it a day, right? In upper level math classes like you're in now, Algebra 2 is kind of getting to be an upper level class. We don't want decimals, right? We don't want we don't want anything where we have lost precision. So the most precise answer you could give is the answer that still involves e. And this is as simplified as it gets. So just give that. Anyway, moving on. So how do I sketch my graph then? Well, we just saw that we're going to be screaming up, 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 up. We're not even going to hit the y-axis until some point that's way off the grid. Then here we're coming down, down, down. And just show me that you get that we should be approaching the asymptote, never quite touching it. This is not the best sketch I've ever seen, but it's good enough. Okay. Now that we've got a sketch, we can address all of the other properties. For domain, we probably should have known a while ago that that was all reals, because every exponential has a domain of all reals. We can see it now. Our range is definitely going from the asymptote up, so that means it'll be from -1 to infinity. Now, we use hard brackets and soft brackets sometimes, but hard brackets mean that the value is in our range. -1 is not in our range because we never actually hit -1, so you want soft brackets, but that's our range. Next, we want to know what interval we're increasing on, and this function never increases. It's decreasing the whole time. So for increasing interval, you'll say none. And for decreasing, remember you're giving the values from the x-axis that tell where the decrease occurs. It has nothing to do with the y values. So we know that we decrease on the interval that starts all the way at -infinity, and we don't stop decreasing until we go all the way to +infinity, and that's that. Boundedness, you might remember, is basically a multiple choice question. We can be bounded above, we can be bounded below, we can be bounded, or we can be not bounded. And I told you in class that when it comes to exponential functions, you actually can't ever be not bounded. You're always going to have a top or a bottom. And you can't be bounded because that would imply you have both a top and a bottom. And one of your branches is always going to go to infinity or -infinity. So boundedness is honestly just a coin flip. You're either bounded above or you're bounded below. And we can see in our graph that this guy's bounded below. So give me that as your answer. In terms of end behavior, end behavior, left end behavior at least, is going to always be as x approaches -infinity. -infinity is off here to the left, right? So that's what you'll say. And then you tell me what is y doing? What value is y approaching? And right end behavior is similar. You'll say as x approaches +infinity, the y value is approaching something. And again, looking at the grid, if we were to ride this function as far to the left as we could go, we see that the function will take us up, 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 up to +infinity. So your left end behavior is that y goes to infinity. Your right end behavior is that if I follow this function as far as I can to the right, I eventually get stuck at the asymptote, which is down at -1. So that's that. And then finally, it says list all of the transformations from the parent function. Well, the parent function would be what you get if you strip away all the other transformations. So it would just be e to the x. If my parent function is e to the x, then that means the 2, the 3, this negative sign, and this -1 all represent transformations. So there's certainly going to be 4 transformations. Can we see all that? Yes. And what are they? Well, remember, the general rule for transformations is you always list your translations. They should come last, because if you translate before you reflect or before you dilate, you can mess stuff up. So look in here. Where would I start? I guess just start with A and kind of just go. So that 2 represents a vertical dilation by a factor of 2. And then the 3 can be a little tricky if you don't rewrite the function. So I would recommend that maybe you rewrite this. And I'm going to make a little room up here. So if we take our exponent and rewrite it as -x plus 3, then that's a good start. My base would still be e, my coefficient would still be 2, and I'd still be subtracting 1. But actually, even in this form, we're not quite done. We would want to factor the negative out. So it would actually change this to a minus, and we would have 2e to the negative x minus 3 minus 1. And if we do all that, then we can see that this negative sign is a reflection over the y-axis. And then the -3 and the +1 are both translations, so we'll do them last. So the -3 will translate us right. So translate 3 units right. And then translate 1 unit down. And that's finally everything. Okay, so I hope that made sense. If there's any part that didn't make sense, then you'll want to find me before class. I'll try to give you a couple minutes before we take the quiz so that you can ask any questions if you need to. But as we move on to the next one, I'm going to do this one faster because obviously, 13 minutes to do that last problem is a little long. We need to be a lot faster than that. So let's be faster. But I'm still going to do the same steps. I'm going to start with my asymptote, which is going to be y equals -3, because again, you're just looking at the d value on the end. And I'll plot that on my grid. Then I want to find points. And if I want my exponent to be 0, then I'm going to have to let x be -4. And if I want my exponent to be 1, I'd have to let my exponent be, my x value, be -3. So those should be where we evaluate. Plugging in -4 gives 0, and 3 to the 0 is 1. 1 times -2 is -2, and -2 take away 3 is -5. So I can plot a point at -4, -5, and right away we see that we're getting a point that's under the asymptote, which maybe that creeps you out at first, until you notice that, yeah, we have a -a value. -a values are reflections over the x-axis, or essentially reflections over the horizontal asymptote. So since the parent functions are always above, we should expect this graph to be below the asymptote. So I'm not nervous about this at all. Then I plug in -3. 3 to the 1 is 3, times -2 is -6, take away 3 is -9. So at -3, we're getting -9, which is way down there. And then that's supposed to be it. As soon as I see these 2 dots showing me kind of a decreasing trend, I know that this side of the graph should be riding along the asymptote. And then when I get close to these points, I'll quickly take sort of this nosedive down, down, down. And it looks again like even if I extend this y-axis, I'm not going to hit it until I'm pretty far down. So when we do the y-intercept, I would expect to get a pretty big negative number as my y-intercept. Why don't we do that now and find out? Okay, so again, to find the y-intercept, you're going to just plug in 0. The y-intercept will always be f of 0. So if our function is -2 times 3 to the x minus or x plus 4, then we're doing 0 plus 4, and then taking away 3. And you see that yes, this is pretty big because this is -2 times 3 to the 4th. 3 to the 4th is 81. And then doubled is -162. Take away 3 more. That means my y-intercept is way down at -165. But again, looking at my sketch, that actually feels kind of right. We can see that this graph is going down really, really fast. And so even though there's only 3 units left to get us to the y-axis, we're going to go down pretty far before we get there. All right, what else? Now that our graph is graphed, we can say that our domain is all reals. We can see that our range is not from the asymptote up this time. It's from -infinity up to the asymptote. So that's going to be -infinity up to -3 soft bracket. And again, this function only decreases. So my increasing interval is none. And the decrease again occurs the whole time. It occurs from -infinity all the way to infinity. Okay, what's our boundedness? Well, since our asymptote is above the graph, we're bounded above. And BA is fine, bounded above. For end behavior, you're going to want to tell me that as x goes to infinity, -infinity, the function f of x goes toward, and we see that as we go left, the graph approaches the asymptote, which is at -3. Also, as x approaches positive infinity, our function is approaching, well, it's going down, down, down. So the function's approaching -infinity. And finally, we got to list our transformations. And as I look up here, I see the negative. That's its own transformation. Then the 2 is a transformation. The +4, the -3. There's 4 transformations here. First transformation is this negative sign. It's a reflection over the x-axis. And then the 2 is a vertical dilation by a factor of 2. And what else? Just these last 2 translations. So the +4 is going to drag us left, and the -3 will push us down. So we're saying translation 4 units left. And 3 units down. And that's everything for this problem. So there's one more. Yikes. Okay, I'm back. One more graphing problem. This one involves E again, so we'll have to make do without our calculators. But again, we see that our asymptote is at y equals 3. That's where I like to start, so I'll put the asymptote right at y equals 3. Then I want my 2 points, and if my exponent is x, that makes this pretty easy because we'll let x be 0, we'll let x be 1, and those will give us our points. Now 0 is very easy because e to the 0 is 1, 1 times -2 is -2, plus 3 is 1, so 0, 1 is a point for us. And then at 1, we're getting what? -2 e to the 1 plus 3. So that's -2 times 2.72. That's what we're letting e be. Really, it's 2.718 if we go to 3 decimal places, but we're just rounding. So if I double this, what do I get? 4, 5, 44. Same thing we got last time. This time it's negative, and then we're adding 3. that means we're taking 3 away from this, really. So I don't want to screw this up, and I'm really bad at arithmetic sometimes. So what are we doing? 5.44. So our final answer is going to be a negative number that is whatever we get when we take 3 away, right? So it is just this. I'm going crazy. Is it really just that? Yeah, I guess it is. Okay. So negative 2.4, we'll call it. Okay. So the 0.1, negative 2.4 would put us about here. And again, we see that these 2 points show a decreasing trend, which means this side must be the side that's asymptotic. And we run, hitting here, and then going down, down, down real fast. And that's a good looking sketch. Some good news. Our y-intercept is actually one of the points we just found. Our y-intercept is the 0.01. My pen stinks sometimes. 0.1. And then, I don't know, go do the domain and range. Those are easy. Domain is all reals because it's always all reals. The range always involves the asymptote, and in this case it's negative infinity up to the asymptote. So negative infinity up to 3. Then our increasing interval is none because we don't increase, we only decrease. And we decrease from negative infinity all the way to infinity. And our boundedness is that we're bounded above. And our end behavior to the left, we would say as x goes to negative infinity, that's the left direction, y goes to, and it's going to go toward the asymptote, which is at 3. Then the right end behavior would be as x goes to positive infinity, the y goes to negative infinity, because we're going down. And then finally our transformations, and again I see a negative sign, that's a reflection. This too is a vertical dilation. There's nothing in the exponent, but this plus 3 on the end is a translation. So there's only 3 transformations this time. And we'll start with the reflection over the x-axis. Then we'll be vertically dilated by a factor of 2. And then translated 3 units up. And that's it for graphing. Hopefully you feel good about that. And we can move on. So next there's 4 problems about writing the exponential function that passes through these pairs of points. These numbers look a little rough, so maybe you're a little nervous about not having a calculator, but hopefully I'll show you that it's not that bad. Okay, so looking at this first set of ordered pairs, we know that we want to set up a system of equations. Oh gosh. All right, I'm not sure how loud that was, but if you hear screaming, my son is playing Astrobot, and something happened he didn't like. Okay, so we said that to write an equation of the form y equals a times b to the x, what we want to do is take each of the ordered pairs we're given, plug the x in for x, plug the y in for y, and generate 2 equations. So I'll use this first point, and we'll say y is 1/4, and it's equal to a times b to the negative 1. Then we'll take the second point, this one, and we'll say 8 is equal to a times b to the 4th power. And I taught you a couple methods for solving these, but all in all, I think the method where we divide the 2 is just always going to be the best method. I mean, maybe not. Some of you may like the other method, but I'm going to go ahead and keep dividing, I think. And I'm going to divide the red by the green, because if I do 8 divided by 1/4, then that's just going to really be 8 times 4, which comes out to 32. If I did 1/4 divided by 8, we're going to end up with 1/32. It's going to be a little bit uglier. So if I'm dividing red by green, then that means I need to set this equal to ab to the fourth divided by ab to the negative 1. And by dividing these, we get the a to cancel out, right? That just cancels out. And what am I looking at? This would be b to the fourth minus negative 1. That means it's really b to the 4 plus 1, which means it's b to the fifth, which means to solve for b, I just take the fifth root of both sides. And hopefully by now you've memorized that the fifth root of 32 is 2, which means b is 2. Now, to find a, you just take the b that you already found and you plug it back into either equation. In my opinion, the red one looks easier to work with. So I know that 8 is equal to a times b to the fourth. And I know that b is 2. So that means I have an 8 that equals a times 16. And then if I divide both sides by 16, I get 1/2 as my value of a. And then just make sure you give your final answer as an exponential. So remember, it's supposed to be y is equal to a times b to the power of x. And that means our final answer is y equals 1/2 times 2 to the power of x. And that's your final answer for the first one. Okay, I'm back. That's one down. A few more to go. Take that one, shrink it. All right. So the next one, same deal. Set up the equations, divide the equations, cancel the a's, solve for b. I might not even do all 4 of these because you guys will probably get the gist of it real quick. So again, this first one is going to be 20 equals a times b to the 1. And the second equation will be 320 equals a times b cubed. Now, we're just going to divide. We obviously want to put the 320 in the numerator because 320 divided by 20 is going to come out cleaner than 20 divided by 320. So then we'll put ab cubed in the numerator, divide that by a b to the 1, and we'll see that the a's cancel. 320 over 20 is easy as long as you reduce first. They're both divisible by 10, right? So divide by the 10. Then 32 divided by 2 is giving 16. And that apparently equals b to the 3 minus 1. That's b squared. So you take the square root of both sides. And don't forget that technically, when you take the square root, you get a positive root and a negative root. So technically, you get plus or minus 4. But also don't forget what b represents. B is the base of an exponential. And one of the rules about our base was that base has to be strictly greater than 0. It can't be 0, but it also can't be 1. So it really can't be negative 4. That solution is extraneous. It's going to have to be 4 because the base has to be positive. So 4 is b. Then we can take that b, plug it back into one of our equations. Top one is much easier to work with. So we get 20 is equal to a times 4 to the 1. 4 to the 1 is 4. Divide by 4, you get 5. So this time, the equation for number 2 is y equals 5 times 4a. I mean 5 times 4 to the x. That's that. In the interest of time, I'm not going to do the next 2. So moving on. This one says, rewrite each of the following in standard form. Standard form is when you express your exponential just with some coefficient times some base to the power of just plain old x. So that means if my exponent here is 2x minus 1, I got to get rid of the minus 1. I got to get rid of the 2. And we said the way to do that was to use our rules of exponents. So what you hopefully recall is that in the past when we had b to the m over b to the n, that became b to the m minus n. And if you understand how to use that rule going this way, then it shouldn't be too hard to use that rule going this way, because I see a 1/2 to the 2x minus 1. Well, I see subtraction in my power. That means this must be equal to a 1/2 to the 2x divided by a 1/2 to the 1. Because again, this rule right here says that that kind of expression, you keep the base and subtract the powers. So if it works, going from left to right, it has to also work going from right to left. So that's kind of the big thing to understand about these kinds of problems. So to solve this, we're going to go ahead and say y is equal to the -2. Leave that part alone. Then my base of 1/2, we're going to split that and say, well, one of these is 1/2 to the 2x. But then I'm dividing that by a 1/2 to the, not to the -1, just to the 1. Okay. And it actually dawns on me just now that there is maybe a simpler way to do this. So I guess I'll teach it to you. Maybe you can try it out. So rather than dividing, so this is not working. What we could actually do is rewrite this exponent as 2x plus a -1, right? And then I could treat this as an addition problem, because then it breaks down in a way that I think is a little bit easier. We get the 2, then we get a base of 1/2 to the 2x, but now because we're adding, we would multiply by a base of 1/2 to the -1. Maybe this is better. I don't know. It's up to you. So where do we go from here? We still have this -2. I'll just bring him down. Now this 1/2 to the 2x, I would break that down more, because I know that when I'm multiplying in my powers, I can treat that as raising 1/2 to the 2 and then to the x. It's power to a power. Then my 1/2 to the -2, I can apply my negative exponent to this and just take the reciprocal of my base. So my base becomes 2 and my power becomes positive. So round about now, we're just about done. I hope you're noticing that these 2's can just combine. They can just be multiplied to make a coefficient of -4. And then here I can square the base of 1/2, so it becomes 1/4. And we're raising all that to the power of x. And now this is us in standard form. We made our exponent only an x, and we just have our coefficient in our base. So that's the form you're trying to get to. So let's try 6 now. And 6 really only has the one thing. It's just a product. And when you see a product in your power, you want to break that down as power to a power. So this would become coefficient of 5. The base stays 2. And we're raising that to the power of -2, but raising that to the power of x. So it's like power to a power. So we now have coefficient 5. Then the -2 would flip our base, take the reciprocal of it, and still be raising it to the power of 2 to the power of x. And then 1/2 squared is 1/4 to the power of x. And there we are in standard form. All right, and then the last one, we see it's an addition problem. So we would break this down to be a 3 times a 2 to the power of x times a 2 to the power of 3. Because we know when we have a sum in our power, that must have been a product of the 2. So to break this down, this would be, well, that's still just a 3. This is still just 2 to the x. But a 2 cubed makes an 8. And because that 8 is a whole number, you would just go ahead and combine that with the other whole number. Just do 8 times 3 and make your coefficient 24. And that's it. Yep. All right, moving on. Okay, so finally this was one of the topics I was a little nervous for you guys. But if we are trying to evaluate these, my advice is still to just sort of say, okay, I want to know what this log is worth. It equals something. And what it equals is the power that I'd have to raise 2 to get 128. And you might not know that off the top of your head. Honestly, I didn't really know it off the top of my head. But I do know 2 to the 5th. I've got that one memorized. 2 to the 5th is 32. And that means that 2 to the 6th would just be 32 times 1 extra 2. So 64. And that means 2 to the 7th is 64 times 1 extra 2. So 128. So there you go. It's 7. And so since 2 to the 7th is 128, we know that this entire log just equals 7. And if you can do that in your head, then I don't need to see any work, really. You don't have to show me anything. You would just say, this expression equals 7. And 7 is honestly the only thing I need to see. Because for something like 9, this one should be obvious. This log is saying, what power should you raise 4 to get 64? And I should cube it, so the answer is 3. Okay. Over here, it's a little trickier. The relationship here is that the square root of 9 is what would give 3. And square roots are powers of 1/2, right? So if this log is looking for the power of 9 that gives 3, that power would be 1/2, so that we take the square root of 9 and get our 3. Another tricky one. Again, you're looking for a power of 5 this time. That gives 1 over 125. And if you think about it, 5 cubed is 125. So to get to 1 over 25, wouldn't we just use -3 as our power? Then the negative would take our reciprocal, the 3 would cube us, everything would come out great. So we know that the value of this log is -3. Then for 12, there's a bit of a trick here. You may not have known this, but I sure hope you did. If you see a logarithm without a base attached, then that base is understood to be the number 10. It's called the common logarithm. Common log is a log with a base of 10. And we're doing the log base 10 of 1 over 100. And this one is really similar to 11, honestly, because you're probably noticing that 10 squared would give 100. But we don't want 100. We want 1 over 100. So again, just let the exponent be negative. And the negative will take the reciprocal of your base. The 2 will square it and turn it into 1 over 100. So again, final answer here is just the -2. Okay? All right, now 13 is using this new symbol ln. It stands for the natural logarithm. So every ln that you ever see, it just means that you're doing the same logarithm that we did in every other place, but the base of this log is the number e. So that's the natural log. It's a log whose base is e. And we're doing log base e of square root of e. But what's the square root of e? Square root of e would be e to the 1/2 power, right? So again, this question is just saying, what power should I raise my base of e to get e to the 1/2? Well, it's obviously 1/2. Right? So the answer there is 1/2. And next, this is another log base e question. And they're wondering what power of e gives 1. Well, it's the same power that makes anybody into a 1. The only thing that you could raise e to get 1 is 0. E to the 0 is what would make 1. So this logarithm equals 0. And finally, this is another common log. It's a log whose understood base is a base of 10. So again, we're wondering what power of 10 is going to give us 1,000. And I don't know, think about it. 10 to the 1 is 10. 10 squared is 100. 10 cubed would just be like an extra 0. Oh, I see. The number of zeros is equal to the power that you're raising 10 to, right? So if you had a 1 with 7 zeros, that would just be 10 to the 7th. But again, we see that the exponent we want is 3. So that's the value of our log. Okay, next. It says simplify and leave e in your answer with no negative exponents. So if I'm simplifying this, then I'm just remembering that this 3 would distribute onto both of the factors in parentheses. So I'd end up with a 2 cubed times an e to the 5th to the 3. So 2 to the 3, I can just evaluate that. That comes out to be 8. But this guy that involves e, rather than trying to actually figure out the value, I'll just use my properties of exponents, and I'll say power to a power, I'm multiplying. So I'm going to have an e whose power is 15. And that's it. That's your final answer. Next. Looking at this guy, I would certainly in my mind break this apart to just be 8 over 2 times e to the negative 4 over e to the negative 2. Now the 8 over 2 is certainly just 4. How do I do this? Well, I'd keep my base and subtract my powers. So it's negative 4 minus negative 2. That means negative 4 plus 2. That means it's still negative 2. So you get 4e to the negative 2. But it does say up here, no negative exponents. So we need to know that when you have a negative exponent, you just kind of take the reciprocal of your base, right? So this is like having a 4 times a 1 over e. And that 1 over e is getting squared. So it would be 1 squared over e squared. But 1 squared is just 1. But I'd put this 4 over 1, put everybody back together. We see that our final answer is a 4 in the numerator and an e squared in the denominator. And that's the answer to 18. Super psych. That's the answer to 17. Okay, so 18. These parentheses may only be confusing people, right? They're showing you 2e to the 5th like it's one whole thing. Then they're showing you negative 3 e to the negative 5th like it's one whole thing. But honestly, what I see when I look at this is a 2 and an e to the 5th. And the negative is almost its own thing. It's like just having a negative 1 times a 3 times an e to the negative 5th. And once you kind of separate everything out, I see whole number, whole number, whole number. So I certainly want to just multiply all that together to get back to a negative 6. Then I see e to the 5th times e to the negative 5th. Pretty sure the rule for that is keep the base and add the powers. But that gives me negative 6e to the 0, which is just going to be negative 6 because it's negative 6 times 1. So that's it for those kinds of questions. And so finally, we get to the questions about writing inverse functions. And to write this inverse function, we know our first step is to flip the variables. So this y variable becomes x. And then in the log, instead of x plus 1, we're going to see y plus 1. Okay, so this now is technically my inverse function, but we're not done until we get y all alone. So before we do anything, we have to get this whole log expression alone. And that just means subtracting 2 from both sides. Okay, so once you get your log alone, really the only way to sort of isolate the y and get it out of here is to convert between logarithmic notation and exponential notation. So remember, when we convert, the base of the log stays the base of the exponential. Now I don't see a base, but when I don't see a base, that means the base is understood to be 10. So when I go to convert this to exponential, 10 is going to be my base. Then there's some power on 10, and the whole thing is equal to some other thing. And it should be pretty clear that there's only two other things. There's x minus 2, there's y plus 1. Yeah. So where do you think each thing goes? Well, the answer is the thing that you were taking the log of, that's actually what the exponential is going to equal. And the thing that the log equaled, that's what's going to be in your power. So you're going to have 10 to the x minus 2. And that's going to equal y plus 1. So from here you could just subtract the 1 to get 10 to the power of x minus 2 minus 1. Sound good? Hope so. And that equals y. But we said we're going to flip-flop that. And instead of y, say f inverse. But we're done now. The inverse of this log function is this exponential. So it won't be too shocking. When we find the inverse of this exponential, it's going to be a log equation. Okay, but still, same first step, which is turning the y variable into an x variable, and then turning all the x variables into y variables. Okay, so what do we do now? Just like over here for 19, we wanted to isolate the log. Over here, we want to isolate this exponential, which just means this 4 has to go. So you'll subtract 4 from both sides, getting x minus 4 equals this exponential expression. And again, the only way to get y out of the exponent is to kind of convert from here to logarithmic notation. And again, our log will always have the same base as our exponential. So we'll put a 3 down there. Then we are taking the log of whatever this exponential equaled, so the x minus 4. Then what this log is supposed to equal is whatever power we had on 3, so y plus 1. And then to get to a final answer, just subtract 1 from both sides. So your final answer is log base 3 of x minus 4 minus 1. And that would equal f prime. Okay, that's it. I think that's the whole review. So just go back and study, and I hope you'll be ready by tomorrow. Thanks. Have a good night.